Good afternoon. I'm Fiona from the FEKO marketing team, and I'd like to welcome everyone to our first FEKO webinar for 2014. A recording of this webinar will be available within 24 hours, and a notification email will be sent to you providing a link to the presentation. We encourage you to post questions for the presenter throughout the presentation in the area provided on the right-hand side of your screen. You do not have to wait until the end of the presentation to post your question, but Gopi will only answer them at the end of the session. For further information on FEKO, please visit our website or contact your local distributor. You're also welcome to contact us via the email address that appears at the end of the presentation, webinars@emss.co.za. We introduced Gopinath Gampala, a Senior Application Engineer in our EMSS USA office located in Virginia. He will now present the webinar entitled Radome Analysis Techniques in FEKO. Over to you, Gopi.
Thank you, Fiona. Good morning, everyone. My name is Gopinath Gampala. I'm a Senior Good morning, everyone. Thank you, Fiona. My name is Gopinath Gampala. I'm a Senior Application Engineer with EMSS USA. Today, I will be discussing about advanced computational electromagnetic tools for the analysis of electrically large radomes. Actually, we get inquiries from our customers as well as potential customers on a regular basis regarding the capabilities of FEKO for the analysis of radomes. That is why we put together this WebEx to demonstrate the power of FEKO for the design and analysis of radomes. But before we jump into that, let me give you a little introduction about radomes and their applications. What is a radome? A radome is a structural weatherproof enclosure that protects an antenna. It prevents ice and freezing rain from accumulating directly onto metal surfaces of the antenna. It also protects antennas from debris and rotational irregularities due to wind. So this is from a mechanical point of view, but from the electromagnetic point of view, it minimally attenuates the electromagnetic signal transmitted or received by the antenna. So an ideal radome should be transparent to the RF signal. These radomes can be constructed in several different shapes depending on the application. So let's look into some of the applications. Radomes are used on aircrafts, so every aircraft has a weather radar as well as antennas for communication. So all these antennas are protected by the radomes. Radomes are also used on missiles, so the missile tracking radar is protected by the radome. They are used in maritime applications, commercial telecommunications, vehicular communications, air traffic control, satellite communications, and weather radar applications. So since radomes find applications in wide variety of industries, that is why I believe we get inquiries from our customers on a regular basis. So what are we focusing on today? So today we will be looking into factors affecting the radome, different types or styles of radome, radome-induced effects, characterization of radome wall materials through planar Green's functions, and periodic boundary conditions. Then we will look into the radome analysis techniques, namely the method of moments, multi-level fast multipole method, relaunching geometrical optics, and thin dielectric sheet approximation. So when we are looking into TDS, we will look into examples of TDS with MLFMM and relaunching geometrical optics. Then we will look into a real-life example of a airborne radome. So for this study, we chose the Airbus A380-800. This will be followed by the conclusions. So what are the factors affecting the radome? Radome wall thickness is obviously a factor. So in general, thin walls are considered to be better, and the radome wall design as well. So the number of layers and thickness of each layer affects the radome. In general, more layers are considered to be better. The more the number of layers, the more variables the designer has to play around with. So it gives more flexibility in designing the radome. And the radome shape, so the curvature of the radome affects the performance of the radome. So in general, flatness is desirable, but we all know it's not possible in all situations. And the selection of radome materials, permittivity of each layer also affects the radome. So that is why it is always recommended to choose materials with a small loss tangent. So now that we looked into the factors affecting the radome, let's see what are the different types of radomes. On a broader scale, radomes can be classified into monolithic and sandwich designs. So the monolithic, by the name itself, it's a single layer design, and there are several types of sandwich designs like the A or B sandwich design where we have 3 layers, or the C sandwich design where we have 5 layers, and beyond C sandwich we have multi-layer dielectric wall radomes. So we will look into the monolithic as well as the sandwich radomes in details. So first let's look into monolithic wall types. There are 2 types of monolithic radomes. First one are the half-wave radomes, which are also called style A radomes. Inherently these are narrowband radomes. Typically the bandwidth is less than 5%, and the bandwidth reduces further for radome wall thicknesses of multiple half wavelengths. And the second type are thin wall radomes. These are also called style B radomes. In general, the wall thickness of these radomes will be approximately 0.1 wavelengths. And these radomes are particularly useful for transmission instant angles ranging from 0 to 70 degrees measured from the surface normal. And these monolithic radomes are a popular choice for airborne applications. And the next are the sandwich walls. So there are several different types of sandwich constructions. For the first one is the A sandwich radomes, which are also called style C radomes. So here high dense skins are separated by less dense core. These offer high strength to weight ratios and good electrical performance at low incidence angles, and these are popular choice for airborne applications. And the next type are B sandwich radomes. These are also called style E radomes. So unlike A sandwich, here less dense skins are separated by a high dense core. So since on the outer surface we have a less dense material, which is a less dense skin, these are not useful for airborne applications, and that's why these are limited for terrestrial applications. And the next type are multi-layered wall radomes. These are also called style D radomes, so where we have 5 layers and 7 layers. So what is the advantage of increasing the number of layers is most of the time it increases the transmission bandwidth. And since we have more number of layers, now we have more variables to control, so that gives more flexibility in design. But increasing the number of layers also introduces greater insertion phase delays. This results in higher Boresight error values. We will see what is Boresight error at a later stage. So now that we looked into different types of radomes, so let's see what are the radome-induced effects. What happens whenever we place a radome on top of an antenna? So because of the radome, it changes the electrical performance of the antenna because of the dissipative losses within the dielectric material, and also because of the electrical phase shifts introduced by the presence of radome, and also because of internal reflections. So all these factors, they manifest themselves into radome performance parameters. So if you want to measure the performance of a radome, you can measure it in terms of radome insertion loss or simply radome loss, and also in terms of antenna sidelobe levels and Boresight error. So let's look into each of these radome performance parameters. So first, radome insertion loss. Radome loss is nothing but reduction in signal strength as the electromagnetic wave propagates through the dielectric radome wall. And this loss occurs partly because of reflections at a dielectric interface, and the remainder of the loss occurs from dissipation within the dielectric layers. And the loss tangent of each material is a measure of the dissipative losses. So that is why we always recommend to choose materials with low loss tangent. And the next one is antenna side lobe levels. So generally, whenever you place an antenna inside a radome, it increases the antenna side lobe levels. And that is because of the wall transmission effects as the wavefront propagates through the radome wall, and also because of wavefront distortion. So whenever we are designing the radome, we need to make sure that the side lobe levels are not increased dramatically. And the next is the Boresight error. It is nothing but the bending of angle of arrival of a received signal relative to its actual angle of arrival. So if you have the antenna or the antenna array where the main beam is pointing in a certain direction, and when you place this under a radome, now the main beam may be pointing in a different direction. And this error is very critical in applications like missile tracking. And this error occurs because of the distortion of electromagnetic wavefront as it propagates through a dielectric radome wall. and this depends on frequency, polarization, and antenna orientation. So now that we looked into the radome performance parameters, let's see how we can design the radome. The first step in designing the radome is selecting the materials. So when you want to design a radome, first you need to select what type of radome you want to. Let's say if you want to design a multi-layered wall radome, then you need to select the materials. So once you select the materials, you want to characterize the materials. So these materials can be characterized through the analysis of transmission loss. And to do this transmission loss analysis, FEKO offers two fast methods, namely the planar Green's functions and the periodic boundary conditions. So when we look into planar Green's functions, here we can model all these dielectric layers numerically. So we are not going to model any physical layers. We define all the different dielectric media, and then we use the Green's functions to model all these layers, where we specify the order of the layers as well as the dielectric constant of each layers and the loss tangent as well as the thickness of each layers. Then we can calculate the transmission reflection coefficients and look into the transmission performance. So since there are no physical geometries, there are no physical unknowns. So this is highly efficient in terms of memory and time. And the other method is periodic boundary conditions. So unlike Green's functions, here we will have a physical geometry, but we are not going to model a large geometry. Rather, we will model a small unit cell, where within the unit cell we will specify all the different layers, their dielectric constant as well as the thickness, and we will define the periodic boundary around this unit cell. Then this unit cell will be repeated in the plane, and we will be able to realize an infinite layer for which we will be able to calculate the transmission and reflection coefficients. But since we have a physical geometry here, then we will be discretizing it and it will result into some unknowns. So it may take slightly more memory and time compared to Green's functions. Then in that case, what is the use of periodic boundary conditions? Why we need to go to PBC is, so sometimes we design the radomes together with the frequency selective surfaces. So if you want to do the transmission loss analysis together with the FSS layer, then we recommend to go with PBC, because if you are going with Green's functions, you can model all the dielectric layers using the Green's functions without any physical unknowns. But the FSS layer, it should be modeled physically. So you need to model a large layer. So when you are modeling a large layer, it will be discretized and it will result in a huge number of unknowns. So it may take more memory and time. But with the periodic boundary conditions, you can model the FSS layer also within this unit cell. Then it will be repeated so that you can realize the infinite layer of all these different dielectric layers as well as the FSS layer. So whenever you have an FSS geometry together with the dielectric layers, we recommend to go with periodic boundary conditions. But since we are modeling only a small unit cell rather than a bigger one, it doesn't take much resources. So there is a huge reduction on number of unknowns. So it will be also fast compared to modeling a huge finite size geometry. So let's see how accurate these two methods are. So let's compare these two methods. So for this purpose, let's consider a monolithic thin wall radome. This is the layer configuration where we have the dielectric constant of 4 and the loss tangent of 0.015. So on the left we have the radome layer designed using the special or the planar Green's functions, and on the right we have the radome layer designed using the periodic boundary conditions. So here we are trying to calculate the transmission loss for a wide range of incidence angles, and we will compare the transmission loss for the Green's functions as well as the periodic boundary conditions. So let's see how they are comparing with each other. So here you can see the red curve is the special Green's functions or the planar Green's functions, and the blue one are the periodic boundary conditions. Now you can see for a wall thickness of 0.1 wavelengths, they are agreeing very well with each other. In fact, they are overlapping on each other for a wide range of incidence angles. So if you increase the wall thickness, once again you can see they are as accurate as each other. So there is no difference between these two techniques. So it only depends on what kind of radome you have. If you have just the dielectric walls layers, then you can go with the planar Green's function. But if you want to model it together with the FSS layer, then go with the periodic boundary conditions. But these two techniques are within FEKO. So we are comparing two techniques within FEKO and we are judging their accuracy. But let's see how FEKO compares with what we have in literature. So let's consider an example of a sandwich radome. So here you can see the A sandwich layer. We have the dense skins as well as a less dense core but a thicker one, so which is modeled using the planar Green's functions. And here this is a layered configuration. So you can see the skins are made of quartz polycyanate, and the core is the phenolic honeycomb. For the skins, the dielectric constant is 3.23 and the loss tangent is 0.016 and the thickness is 0.7 centimeters. And for the core, we have dielectric constant of 1.1 with a loss tangent of 0.001 and the thickness is 1.01 centimeters. Let's see the transmission loss performance for both the polarizations of the incident plane wave. So here we have the transmission performance at different incident angles over the frequencies, wide range of frequencies. So this is in one polarization. So let's see how this is comparing with the literature. So on the right you can see the published results. So you can see FEKO results are agreeing very well with the published results. So for all the incident angles and for all the range of frequencies, you can see FEKO results are agreeing very well with the published results. And in the orthogonal polarization as well, now you can see FEKO results are agreeing very well with the published results. So you can see there is no difference between the FEKO results and the published results. So you can see this confirms that the planar Green's functions are accurate as well as the period boundary conditions are accurate. So they are as accurate as each other and they are also agreeing very well with the published results. So now that we looked into how we can characterize the radome wall materials, the next step is, so once you select a layered configuration, you take the layered configuration and you mold that into a radome of certain shape. So when you are molding that into a radome of certain shape, so when you have a completely built radome, and if you want to do the analysis of this completely built radome together with the antenna, so FEKO offers several different methods. So based on the electrical size, so you can see what kind of numerical method you want to use. So if it is electrical small, then you can go with method of moments in FEKO. So you can go with either method of moments with the surface equivalence principle, or method of moments with the volume equivalence principle, or you can use the hybrid method of moments and finite element method. And if this electrical small radome has electrically thin dielectric layers, then you can use a thin dielectric sheet approximation. But the real challenge is whenever you have an electrically large radome. So what happens is, whenever the size of the radome increases, then it results in more number of unknowns. Then you need more memory and time to solve this problem. So to handle electrically large radomes efficiently, FEKO offers several different methods, like the multi-level fast multipole method, the ray launching geometrical optics, as well as the thin dielectric sheet approximation. And whenever you are using the thin dielectric sheet approximation, so the good thing is you can use it with the method of moments, and you can use it with the MLFMM, and you can also use it with ray launching geometrical optics. So here we will look into an example where we compare the thin dielectric sheet approximation treated with MLFMM as well as ray launching geometrical optics. So let's look into these methods. So first let's look into the method of moments in FEKO. So FEKO offers the fully featured method of moments, and it is applicable to metal surfaces and wires, and it is also applicable to dielectric coatings and sheets. It can be used with the dielectric bodies. It can also be used with the infinite planar media. And FEKO also offers AC acceleration, adaptive cross approximation. So what this means is, whenever you have electrical small geometry, so it does not result in huge number of unknowns. But whenever you have an electrically small complex geometry, then because of the complexity, you need to mesh this geometry with respect to the complexity, not with respect to the frequency. Then it may result in huge number of unknowns for a small problem. So whenever you have huge number of unknowns for a small problem, you may need more memory and time. So sometimes you may run out of memory if you have a small computer. Then in those cases, you can activate AC acceleration and still be able to solve this problem well within the available resources. So that is adaptive cross approximation. And FEKO also offers higher order basis functions with method of moments. So what this is, with the default method of moments, we use the RWG basis functions where you need to mesh the geometry with respect to at least lambda by 10. But with higher order basis functions, you can go with a much higher, larger mesh. That means you can have a coarse mesh. So if you have a coarse mesh, that means you are resulting in less number of unknowns. So the less the number of unknowns, the less the resources, both memory and time. So you can save memory and time by going to higher order basis functions whenever it's applicable. And we also offer curvilinear mesh elements with higher order basis functions. So if you have a curved geometry, you don't need to go with flat triangles. So you can approximate the geometry using the curvilinear elements more accurately than with the planar triangles. And we also offer low frequency stabilization with MLFMM. So what this means is whenever you are working at low frequencies like kilohertz or sometimes even in hertz, so you can activate the low frequency stabilization. So without low frequency stabilization, when you try to solve a problem at low frequencies, then the solution may not be stable. The matrix may not be well conditioned and the solution may not be stable. So in those cases, FEKO will throw you some warnings, then you can activate low frequency stabilization in MLFMM. So whenever you activate this low frequency stabilization, FEKO will add additional basis functions on top of the default RW basis functions like the loop star basis function. So that will add more stability to the solution. So that is extremely useful whenever you are working on applications at low frequencies. So before looking into an example, let's see how MLFMM works. So I'm not going to complete details about MLFMM, but I just want to give you a brief history of what happens in the background. So whenever you solve a problem with MLFMM, so in the background it will form an electric field integral equation where the unknowns are the surface current. So whenever you are trying to solve a problem with MLFMM, it will always try to solve for the surface currents, and from the surface currents all the other quantities are derived. So here, since the unknown quantity are the surface currents, so you will try to solve this electric field integral equation by applying the boundary condition, and we will test this at different points on the geometry, which will result into a system of linear equations, and we will solve them in matrix form. So this is how it will look in the matrix form. So we will have an impedance matrix, and we will have the unknown current coefficients matrix, and we will have the excitation matrix. So here we provide the excitation, so this is the known quantity, and the impedance matrix, this defines the interaction between each and every unknown on the geometry. So here this is also a known quantity. The only unknown quantity are the unknown current coefficients. So we can solve this equation by I is equal to Z inverse of V. So the memory and time for a problem depends on the size of this impedance matrix. So the size of this impedance matrix is always n by n, where n are the number of unknowns. So if you have n number of unknowns in your geometry, then the Z matrix will be a square matrix, a dense square matrix, n by n size. So as the electrical size of the problem increases, then the number of unknowns will also increase. So as the number of unknowns increase, then the size of the Z matrix increases. So that is why you need more memory and time with MLFMM whenever you are trying to solve electrically large problems. So that is MLFMM, a brief introduction to MLFMM. So let's look into an example with MLFMM. So here we will consider a Nosecone shaped A sandwich radome. So this is the layered configuration. So for the skins we have a dielectric constant of 4.8 with a loss tangent of 0.002, and for the core we have a dielectric constant of 1.3 with a loss tangent of 0.001. And here the size of this radome will be the base inner radius is 1 wavelength and the height is 1.75 wavelengths. So you can see the radome as well as the Vivaldi antenna array under this radome. So the Vivaldi antenna array acts as the seeker under the radome. And this antenna array is designed for 9.4 gigahertz, so namely the X-band antenna applications. And this is the Vivaldi antenna array pattern. So here we will see how this antenna array pattern will be affected because of the radome. So that's the Radome-Induced Effects. So let's see the Radome-Induced Effects. So now you can see the red curve is the Vivaldi antenna array pattern by itself, and the blue curve is the array pattern with the radome. So because of the radome, you can see the radome is introducing a transmission loss of 0.6 dB, and it is also increasing the antenna side lobe levels by 5.4 dB. But the good thing is it is not introducing any Boresight error. So we don't see any Boresight error, but we have some transmission loss, and the antenna side lobe levels are also increased by 5.4 dB. So, but as the electrical size of the problem increases, now we need more memory and time with MLFMM. So what we can do is FEKO offers the high frequency methods which are more efficient in terms of memory and time, and at the same time accurate as well. So first we will look into the multi-level fast multipole method. So how MLFMM will save the resources compared to MLFMM for electrically large problems is, unlike MLFMM, MLFMM works with a factorized version of MLFMM matrix. So if you have a standard MLFMM, then the Z matrix, the impedance matrix, it defines the interaction between each and every unknown in your geometry. But unlike method of MEMS, now MLFM works with the factorized version. So in FEKO we have the multi-level fast multipole method. So we'll have multiple levels. So at the lowest level, the closer by triangles are grouped into a box, and at the highest level, these boxes are grouped into a bigger box. So you'll have only box-to-box interaction. But at the lowest level, we will have the triangle-to-triangle interaction within the box as well as the triangles surrounding this box. So that is how it works with the factorized version, and that is how MLFMM can save the resources. So here, even though MLFMM is working with the factorized version and saving the resources, we are not making any physical approximations. That means this is as accurate as method of MEMS. So since there are no physical approximations, MLFMM is as accurate as method of MEMS. In fact, MLFMM is nothing but acceleration of method of MEMS. So it is also a full wave solution. So when I say full wave solution, there the Maxwell's equations are solved without any approximations. So that means that's the most accurate answer you can get with any numerical method, whether it may be method of MEMS, or whether it may be MLFMM, or whether it may be FEM, or whether it may be FTTD. All these are full wave techniques. So whenever you use a full wave technique, that's the most accurate solution you can get with any numerical method. And whenever you are using MLFMM for electrically large structures, it is orders of magnitude more efficient than method of MEMS in terms of resources, both memory and time. So let's look into an example. So here we will consider a monolithic thin wall radome. So the layer configuration is dielectric constant of 4, and the loss tangent is 0.015. So this is the radome treated with MLFMM, and the size of the radome is 5 by 10 wavelengths, and the wall thickness is 0.1 wavelengths. And this is the dipole array under the radome, so at 9.4 gigahertz. So now let's see how the radome is affecting the antenna pattern here. So we look into the radome-induced effects. So now you can see the radome is introducing a transmission loss of 1.5 dB, but it is not introducing any Boresight error. And from the curves you can also see it is not increasing the antenna side lobe levels here. So this is with MLFMM. But let's say you have limited resources and you are not able to solve the problem even with multi-level fast multipole method because of the size of the problem. Then what is the option is, we recommend to go with ray-launching geometrical optics. So unlike method of MEMS and multi-level fast multipole method, ray-launching geometrical optics is an asymptotic method. So when I say asymptotic method, it means it involves some approximations. So whenever you are using an asymptotic method, if you model the problem well within those approximations, then you get a solution which is close to the full wave solution. But since there are some approximations, it is much more efficient in terms of memory and time compared to the full wave solutions. So let's see the formulation of ray-launching geometrical optics. So as the name itself suggests, this is ray-launching geometrical optics. So it is a ray-based technique. So here we are no longer trying to solve for the surface currents like method of MEMS. So here from the source, rays will be launched at multiple increments. So if you have a source here, the rays will be launched at multiple increments. Let's consider first, for example, PEC structures here. So as the ray hits the PEC surface, at every interaction point, there will be equivalent sources placed additively at every interaction point. And then these equivalent sources are placed according to the physical optics approximation. So what is physical optics approximation is, J is 2n cross H, where n is normal to the surface and H is the incident wave. So and the total field is the sum of all incident fields as well as the fields due to all these approximate sources, or these are called equivalent sources or the Huygens sources. So this is for metallic structures. Let's see how is the formulation for the dielectric structures. So this is very similar to metallic structures, but the only difference is whenever you have dielectric structures, at every interaction point, instead of just the current sources or the J sources, we'll have both J and M sources placed additively based on the plane wave approximation. So whenever you have a source, rays will be launched at a certain increment, and whenever a ray hits the surface, there you can see equivalent Huygens sources are formed, and these Huygens sources will radiate onto the adjacent surface, and wherever this ray hits the surface, there once again equivalent sources are formed. So eventually the geometry will be replaced with these equivalent sources. Now the total fields will be a combination of the incident field as well as the fields due to these equivalent sources. And this ray-launching geometrical optics is very, very efficient with electrical large structures. The reason being, this is a frequency independent technique. That means whenever you are using this ray-launching geometrical optics, you don't need to mesh with respect to frequency. So whenever you are using method of MEMS, we recommend to mesh with respect to frequency. So use at least lambda by 10, and same with MLFMM. But whenever you are using geometrical optics, you don't need to mesh with respect to frequency. You can mesh with any edge length as long as you are able to capture the shape of the geometry. So let's say you have a large, like 100 wavelengths by 100 wavelengths rectangle. This can be meshed into just 2 triangles, so you don't need to worry about the frequency. So that's the advantage of geometrical optics. So let's look into one of the example. Actually, let's try to solve the same problem which we solved using MLFMM. So once again, we will look into this single layer thin wall radome, where we have the dielectric constant of 4 and the loss tangent of 0.015. And this is the radome treated with ray-launched geometrical optics. Now you can see we are using large triangles here. And once again, the dimensions are 5 by 10 wavelengths with the wall thickness of 0.1 wavelengths, and the antenna array pattern here at 9.4 gigahertz. So if you look into the radome-induced effects, now you can see the radome is introducing a transmission loss of 1.2 dB, and it is not introducing any Boresight error, and the Sidelobe levels are also not increased much here. So this is with geometrical optics. So since we solved the same problem with MLFMM as well, let's compare MLFMM with geometrical optics. So here we can see the red curve is just the dipole array, and the blue curve is radome treated with MLFMM, and the green curve is radome treated with geometrical optics. Now if you see the difference here, the asymptotic ray-launched geometrical optics is differing from the full wave MLFMM solution by 0.3 dB. So if you see the difference in the transmission loss here, this is 0.3 dB. So, but if you look at the pattern here, it is almost very close. It's not deviating much from the full wave MLFMM solution. The geometrical optics is not deviating much from MLFMM. So if you are okay with this discrepancy in the accuracy, let's see how much you can save in terms of resources. So these simulations are carried out on Intel Xeon CPU. Actually, this is a E5 series processor. This workstation has 2 CPUs, each with 8 cores, and the total memory of 256 gigabytes. So with the MLFMM, this problem took more than 30 gigabytes, and I was able to solve this problem in 15 minutes by running in parallel on all the 16 cores. But the same problem with geometrical optics, it took less than 2 gigabytes and it took only 4 minutes. So you can see we're able to save huge resources by going with geometrical optics. But the good thing with geometrical optics is, as the electrical size increases further and further, the accuracy actually increases. It becomes more and more like MLFMM. So it will come more close to the MLFMM solution. So here the size is like 5 wavelengths by 10 wavelengths. But if you have a radome like 20 by 20 wavelengths, now the discrepancy may not be even 0.3 dB. It may be only 0.1 dB or even less than 0.1 dB. So as the electrical size increases, the accuracy of GEO also increases. But this is, so far we are modeling the layers explicitly. When we are modeling the A sandwich radome, we are modeling all the 3 layers explicitly, and when we are modeling the thin wall radome, we are modeling the layer also explicitly. We are not using any approximations here for the layered configuration. But let's say you have electrically thin layers. Let's say the overall thickness of all the layers is less than like 0.1 wavelengths. So what you need to do? So whenever you have these multiple layers where the overall thickness is less than 0.1 wavelengths, then you need to mesh with respect to the thickness, not with respect to the frequency, because the complexity of the geometry takes precedence over the frequency in those cases. So when you mesh these thin layers with respect to the thickness, you end up with very small triangles, so that increases the number of unknowns dramatically. So you need more memory and time. So what we can do in those cases is, FEKO offers the thin dielectric sheet approximation. So with the thin dielectric sheet approximation, all the dielectric layers are replaced with one layer of triangular elements which are treated with special impedance boundary condition. So this is the impedance boundary condition. So what happens here is, instead of modeling all the layers explicitly, we model a single surface, we define all the dielectric media, and we model the layer dielectric where we specify the order of the layers and we specify the thickness of each layer, and then we apply that layer dielectric property to the single surface. So once we apply the layer dielectric property to the single surface, now this is no longer a single metallic surface. It is considered as a thick dielectric surface, and the effects of this surface are included in the electric field inequality equation through the impedance boundary conditions. So for this layered configuration, FEKO will calculate the impedance surface impedance, and it will include that surface impedance in the electric field integral calculations. So that is how FEKO will be able to take into account the effects of all these multiple layers. So since we are not having multiple layers, since there is only a single layer, we don't need to mesh with respect to the thickness. Now we can just mesh with respect to the frequency. So that means there is huge reduction in number of unknowns. So it will be very, very efficient with respect to memory and time. So whenever you have electrically thin layers, we always recommend to use the Thin Dielettric Sheet approximation to reduce the resources. So let's look into an example where we compare the method of MEMS as well as Reliance and Geometrical Optics, both of them treated with the Thin Dielettric Sheet approximation. So here we will consider the example of an A sandwich radome. So you can see the layered configuration. So we have the skin and core and skin. And this is the radome treated with MLFMM with Thin Dielettric Sheet approximation. And on the right we have the radome treated with Reliance and Geometrical Optics, and again with Thin Dielettric Sheet approximation. And the size of the radome is 5 wavelengths by 7 wavelengths, and this is the antenna array pattern at 2.35 gigahertz. So if you look into this A sandwich configuration closely, this is the same A sandwich configuration where we compared FEKO results with the published results. So let's look into those results once again. So here you can see for both the polarizations at 2.35 gigahertz, you can see the transmission loss. So in fact at 2.35 gigahertz, there is not much transmission loss for a wide range of incidence angles in both the polarizations. That means this particular layered configuration should be almost transparent for the RF signal. So let's see if that is true. So if you look into the radome-induced effects, so now you can see the red curve is the antenna array without the radome, and the blue curve is radome treated with MLFMM and Thin Dielettric Sheet approximation, and the green curve is radome with geometrical optics, once again treated with Thin Dielettric Sheet approximation. Now you can see the radome introduced a transmission loss of 0.15 dB, and the good thing here is the ray-launching geometrical optics is coming very close to the full wave MLFMM solution. You can see the gain value is 15.29 with geometrical optics, and it is 15.25 with MLFMM. So there is not much difference here. So even by going with the asymptotic method, we are able to come very close to the full wave MLFMM solution. So let's look into another example. So now let's look into a different shaped radome, an ogive shaped radome at 8.5 gigahertz. So this is the radome. The size of the radome is base radius is 4.5 wavelengths, and the inner height is 16.5 wavelengths. And we have a dipole array acting as a seeker. So this is a dipole array placed on top of a reflector at quarter wavelengths away from the reflector. And the size of the array is 2.2 by 2.2 wavelengths. And this array is directed at a certain angle, theta is equal to 10 degrees. And here for the radome, we will go with the A sandwich configuration. So this is the layered configuration. You can see all the 3 layers. So the 2 outer skins with a thickness of 0.24 centimeters, and the dielectric constant is 4.8, and the loss tangent is 0.002. And for the core, we have a thickness of 0.4 centimeters with a dielectric constant of 1.3 and the loss tangent of 0.001. So let's look into the antenna array pattern before going into the radome-induced effect. So this is the antenna array only. So you can see the dipole placed on top of a reflector at a quarter wavelength away from the reflector. So here, unlike the previous cases, we are also closing the radome. This is not an open radome anymore. So since this is not an open radome, let's look into the antenna array pattern together with the radome base plate. So this is a pattern with the radome base plate. So now let's look into the radome-induced effects. So first we will try to solve this problem with MLFMM, and then we will compare MLFMM results with the geometrical optics. So here you can see the red curve is just the antenna pattern, and the blue curve is the antenna with the radome base plate. So we need to compare this blue curve with the radome present. So now the green curve is the antenna under the radome with MLFMM. So now you can see the radome is introducing a transmission loss of 1.1 dB. And it is also introducing a Boresight error of 2.3 degrees here. So this is with MLFMM. So when we are modeling with MLFMM, here we are not using any Thin Dielettric Sheet approximation. So we are modeling the layers explicitly. So let's solve the same problem with geometrical optics, but instead of modeling the layers explicitly with geometrical optics, let's try to solve it with the Thin Dielettric Sheet approximation and compare the Thin Dielettric Sheet with geometrical optics with the MLFMM, where the layers are modeled explicitly. So if you look into those results, now you can see the red curve is MLFMM with explicit layers, but the blue and green curve are the geometrical optics with thin dielectric sheet approximation, where the blue curve is with the far field pattern source and the green curve is with the spherical mode source. So what we are doing here is, when we are solving the problem with geometrical optics, we are replacing the antenna with its equivalent source. So here in one case we are replacing the antenna with its far field pattern, in the other case we are replacing it with its spherical modes. So if you see here, the spherical mode, so ray-launched geometrical optics with spherical modes is coming very close to the MLFMM solution. So why we are replacing the physical antenna with its equivalent pattern is, so let's look into the resources. So how we compare when we replace the antenna and when we have the physical antenna considered. So if you see here, with MLFMM, this problem took like more than 150 gigabytes, and it took like 4 hours when we are running in parallel using the 8 cores. But when we have the physical antenna with the geometrical optics, this is taking like 95 gigabytes, and it is taking like 4.5 hours, even with 16 processors. So it is taking more time compared to MLFMM, but less memory compared to MLFMM. The reason here is, when we have the physical antenna, then the antenna will be discretized into triangles as well as the wires will be discretized into segments. So now each unknown, each method of means unknown will act as a source for the geometrical optics. So the more the number of sources for geometrical optics, the more memory and time it will take to solve the problem, because from each individual source, rays will be launched at certain angular increment, and there, once these rays hits the surface, there you will see the equivalent sources formed at every interaction point. So we want to reduce the number of sources for the geometrical optics. That's why instead of having the physical antenna, we replace the physical antenna with its spherical mode source. The way we do it is, we solve the antenna by itself in a separate problem, and then we export the spherical modes and we import them in your radome problem, and we, instead of the physical antenna, we import the spherical modes as a source. So the seeker will be the equivalent pattern of the antenna instead of the physical antenna. So when we replace the physical antenna with its equivalent pattern, now we have a single source instead of multiple sources. So since we have a single source, now you can see how much memory and time we are able to save. This is not taking even a gigabyte, it's less than 1 gigabyte, and this is not even taking a half an hour, and by running only on 4 cores, not even on 8 or 16 cores. So you can see there is a huge reduction in resources, both memory and time, by going with geometrical optics and by replacing the physical antenna with its equivalent source. And I always try to stress that ray-launched geometrical optics works extremely well with extremely large structures. So whenever you have a large structure, we always recommend to go with geometrical optics. If it is relatively small, go with method of means. If it is slightly bigger, go with MLFMM. But if it is even large, go with geometrical optics. So here we are able to validate the ray-launched geometrical optics by comparing it with the full wave MLFMM solution. So now that the ray-launched geometrical optics with the equivalent pattern is validated, let's take that approach and let's look into a real life example. So here we will consider the example of an airborne Nosecone Radome. So here for this study, we chose the Airbus A380-800. So this is the full aircraft, and this is the front body, and this is the nose cone. So what is under the nose cone in general? So for all the aircrafts, what is under the nose cone? So if you look under the nose cone, you will see a slotted waveguide array. So this slotted waveguide array acts as the weather radar. So this will be the seeker for the weather radar here. And the nose cone is actually a radar protecting this slotted waveguide antenna array. And the weather radar operates in the X-band, typically at 9.4 gigahertz. So we also designed a waveguide, slotted waveguide antenna array at 9.4 gigahertz. So this is the slotted waveguide array design here. So you can see all the slots and the waveguides with the different sizes. And this is the feed guide under these waveguides. So you can see for each waveguide there is a slot on the feed guide at certain angle. And this is a side view, and this is a full view. Now you can see the feed guide is once again fed with another waveguide from the bottom. So we have only a single feed, but from this single feed we are able to excite the complete array through these slots on the feed guide. So this is the antenna pattern at 9.4 gigahertz. So let's look into what is the configuration that we choose for this radome wall. So here we will try to model the Nosecone Radome as a single layer radome. So this is a a single layer radome. So here we are going with a glass composite, but on the exterior surface of this radome we will have a paint, a typical paint. So the glass composite is made of epsilon r is equal to 4 with a loss tangent of 0.015 and the thickness is 9 millimeters. And the exterior surface is painted with a typical paint with a dielectric constant of 3.46 and a loss tangent of 0.068 and the thickness is 0.2 millimeters. So you can see the thickness, the difference between the glass composite and the paint. So if you want to model this paint explicitly, physically, then it is almost impractical because you need to mesh this paint layer with respect to the thickness. Then you end up with huge number of unknowns. So that is why instead of modeling these layers explicitly, we will try to use the thin dielectric sheet approximation. So let's see how we can model the radome. So but before going into model the radome, for this monolithic layered configuration, let's see the transmission loss performance. So now you can see for a wide range of incident angles, you can see this is offering a very good performance. So the transmission loss is less than 1 dB for a wide range of incident angles. So let's look into the radome design here. So now you can see the radome here as well as the slotted waveguide array and under the radome. But since we want to solve this problem with relaunching geometrical optics, so we will try to replace the slotted waveguide array with its spherical mode source. So we will solve the slotted waveguide array in a separate model, as a separate problem by itself. Then we will export the spherical modes and we will import those spherical modes as a source where we have the radome. So now you can see the radome treated with the relaunching geometrical optics. So once again, the advantage of replacing the waveguide array with its spherical modes is reducing the number of MOM elements for the geometrical optics. So that way we will be able to save huge resources, both memory and time. So let's look into the radome-induced effects. So now you can see the red curve is the slotted waveguide array pattern and the blue curve is the slotted waveguide array under the radome. So the radome is introducing a transmission loss of 0.7 dB, but it is not introducing any Boresight error. So, but this is at a certain incident angle, but the weather radar, it's not going to operate at a single incident direction, but it scans over a wide range of angles, typically 60 to 90 degrees. So the tilt feature permits the crew to adjust the vertical projection of the beam, typically 10 degrees up or down, and the antenna itself, it's a mechanically steered slotted waveguide array. So this typically steers from like 60 to 90 degrees either side of the aircraft. So in FEKO, you will be also able to do the beam scanning. So let's see how it performs over a wide range of incident angles. So this is at -60, -45, -30, 15, 0, once again 15, 30, 45 and 60 degrees. So you can see we are able to solve the radome problem, completely built radome together with the antenna, as well as we are able to do the beam scanning as well. So if you want to summarize the numerical methods available in FEKO to analyze the radomes, so if you want to do only the if you want to only characterize the radome wall materials, then you can go with either planar Green's functions or the periodic boundary conditions based on if you only have the layers or if you have the layers together with the FSS. But if you have the completely built radome based on the electrical size, you can go either with the method of MEMS or you can go with the MLFMM or you can go with the relaunching geometrical optics. And if you have electrically thin layers, we always recommend to use the thin dielectric sheet approximation. And whenever you are using the geometrical optics, we always recommend to replace the physical antenna with its equivalent source to reduce the number of sources for the geometrical optics. So in conclusion, we looked into radomes, their applications as well as different types or styles of radomes. Then we looked into how we can characterize the radome wall materials through special Green's functions as well as periodic boundary conditions. And then we looked into the fully functional methods offered by FEKO for the analysis of completely built radomes, like method of MEMS, MLFMM and relaunching geometrical optics. So these methods are presented with the examples. We also looked into the thin dielectric sheet approximation, and we validated this approximation by comparing with explicitly modeled layers. And then we looked into a real life example of an airborne Nosecone Radome for weather radar applications. So thank you everyone for taking time and attending this webinar. So if you have any questions, you are very welcome to post your questions. So you can send us an email at webinar@emss.co.za. And I believe some of you have already posted the questions during the webinar. So first I will try to read the question before I can answer it within the time limit. So the first question here is, this is from Swapnil. So if the element in PCB case is wrapped around a curved surface, so I'm not able to interpret the question completely here, but I believe like if you have a curved surface, if you want to do the transmission loss analysis, the best bet will be to go with the periodic boundary conditions, because if you are modeling with if you are trying to go with the planar Green's functions, so you can model only planar layers, but you won't be able to model the curved surfaces. But by going with periodic boundary conditions, you will be able to model whatever you want to model within this unit cell. And let me see if I have any more questions. They will be extremely complex. So I can see a question where somebody asked whenever he is modeling this A sandwich configuration radome, so he's having trouble to model these skins because they are extremely thin. So as we discussed during the WebEx, whenever you have extremely thin skins, so instead of trying to model them as explicit layers, we always recommend to go with a thin Dielectric sheet approximation. And with the thin Dielectric sheet approximation, if the radome is electrically large, always we recommend to go with ray-launching geometrical optics, because whenever you are trying to use the thin Dielectric sheet approximation, so and if you want to use it with either MLFMM or MLFMM, then the overall thickness can't be more than like lambda by 10. But when you are going with ray-launching geometrical optics, now the thickness constraint is more forgiving here. So you will be able to model layers which are thicker than 0.1 wavelengths when you are going with geometrical optics, because here when we are using this thin Dielectric sheet approximation, internally it assumes a normal instance of the wave. So when you have the physical antenna and when you have fields emanating from the antenna, so all over the radome you won't have this normal instant. But whenever you are going with geometrical optics, since it is a ray-based method, from the source rays are launched at certain increment. So since these rays are hitting it all over the radome at certain angles, now at every interaction point it will be almost like a normal incidence. So that's why this approximation works very well with geometrical optics. So that, and you will be able to use this with thickness greater than 0.1 wavelengths as well, because now you no longer meshing with respect to lambda by 10. So when you can mesh with an edge length which is greater than lambda by 10, then FEKO will be more forgiving, because internally it will do a check and it will compare to see the thickness with respect to the mesh size, and since you have a larger mesh, then it will be more forgiving. So whenever you have extremely thin layers, we always recommend to go with ray-launching geometrical optics and thin Dielectric sheet approximation. So somebody asked about for FEKO versus literature, are simulation times available when using planar Green's functions versus periodic boundary conditions? So yes, we do have those available. So if you can please send us an email, we will be able to share those timings, as well as those are not confidential models, so we will be able to share the models as well. And somebody asked, please restate frequency range for using low frequency stabilization with MLFMM. So whenever you are using low frequency stabilization with MLFMM, so in general you can try to solve it directly, but whenever the solution is not stable, FEKO will throw you warnings in the execution window. So like the solution is not stable, switch back to double precision. Whenever you see those kind of warnings, then you can go back and you can activate the low frequency stabilization as well as a switch from a single precision to double precision. But if you don't see any of these warnings, then you can be confident of your solution. So I believe we are close to the end of the WebEx here, but I will try to answer one more question here. So somebody asked, like, I would need to characterize both low and high density materials, or design a tapered progression of low permeability layers and corresponding low loss tangent layers. So whenever you have a tapered design, so obviously you won't be able to use the thin dielectric sheet approximation, because the thin dielectric sheet approximation, it assumes uniform thickness all over the place. So in those cases, unfortunately, you will be you need to go with modeling explicit layers. But if you have uniform thickness layers, then you can take advantage of the thin dielectric sheet approximation. But for tapered designs, so you need to go with explicit layers based on the size. You can go with either method of MEMS or MLFMM or Geometrical Optics. So I once again thank you everyone for attending the WebEx. So if you are not able to answer any of your questions, so please send us your questions. Please email to webinar@emss.co.za, and we will try to get back to you as soon as possible. So thank you everyone.